Hello and welcome. This is another ground-based infrared telescope called the Infrared-Optical Telescope Array I want to discuss today. This is again the outline of the presentation. First history, and then the equipment, geography, some results of the telescope, and then summary and outlook. The IOTA was opened up in 1993 with 2 telescopes, and the 3rd telescope was added in 2000. But it was stopped at 2006 due to lack of funding. Sounds sad, but we will see later that this is not actually so sad. And why? These research institutions have worked together to set up the telescope, so some of them are really powerful, because probably it was expensive, not like today's telescopes, but for the time. And the aims were to do experiments on technique, because interferometry with the infrared light was still difficult back then. For the radio telescopes it has been used before that, because the longer the wavelength, the easier interferometry is. People looked at the form of giant stars like Mira-stars or Cepheids with their telescopes. Well, I'm going to show you a little bit of that later. And it was also very good for separating double stars. The equipment was 45 centimeter mirrors that were positioned in an L shape, with the short arm being 15 meters and the long arm 35 meters. So in an interferometer, the resolution of the image doesn't depend on how large the telescopes are, but the distance between the telescopes. But first, in order to do that, you have to make sure that the light can be interfered in a central point somewhere, and the distance from the mirrors to the interference patterns is exactly matched, so you get a nice interference pattern like this. Detectors used were Indian anti-moon telescopes sensors first, and then they were replaced by this mercury cadmium tellure detectors for the near infrared. Near infrared means between 1.1 and 2.5 microns, but there were also CCDs for the visible light. The geography of this telescope is very impressive. It was located at the Fred Lawrence Whipple Observatory on Mount Hopkins, well known for a 6.5 meters multi-mirror telescope that is situated up there. I couldn't find out whether it was here or here, because both points are labeled with Whipple Observatory on the Google Maps. And especially here you can see how dry the observatory is and why. It's not only relatively high up, it's also in a valley that is in the wind shadow of a chain of mountains. That's always very good for dry climate. We will see this later also with the Gornergrat Observatory. So often it's not best to be on the peak of a mountain, but rather some kilometers on the backside of a chain of mountains. But 31 degrees north is really eternal high pressure zone, which is called like this, but it's not strictly true for the whole year, but for most part of the year. For example, they looked at these Mira-type variable stars. There's a paper by Ragland where he looked at 35 Mira-type stars, all within 1,300 light years, because they had to be resoluted by the interferometer. And these stars show this pattern with the two different types of maximums that are alternating. So there's a 4th magnitude maximum and a 6th magnitude maximum, and in between the stars could go down to a minimum that is very weak. For example, for Mira, if it's in the minimum, you can't see it by bare eye, but in the max, around the max, you notice, oh, there's a star there. Mira is the most well-known example, but there are more of these long period variables. And the radius that these stars have depends actually on the wavelength of light you observe them, because their atmospheres have molecules in there, and sometimes the atmosphere blocks the light and sometimes it lets it through. So this is how that works. Not like the Cepheids work, but it's about the atmosphere of these stars, and these diameters can be measured, and also if the light is symmetric or not. And this is what Ragland did in his paper. But people made also pictures of Arcturus, and the diameter of Arcturus is roughly 21 milli-arcseconds. Here you can see the milli-arcsecond scale. So interferometers are the first telescopes that make it possible to properly see stars, not as one point, but as an array, as a matrix of points. By the way, the ESO telescope that is being built at the moment should have a resolution of 10 MAS or better, so it should see Arcturus as 4 adjacent pixels actually. But these interferometers are even a bit better than that. And interestingly, they could also exclude a companion of Arcturus within one astronomical unit. And they were not quite sure, but if they had seen a marginal water vapor emission around Arcturus. So that's what you can do with these type of telescopes that have really high resolution. But the IOTA had relatively small mirrors, and this is actually, I think, the reason why it was discontinued, because larger telescopes have used the same technique now, and this is how it looks if you take a interferometric picture of Antares. So you can really see the star, the form of the star, and also some bright and dark spots on the star. Of course, Antares is a very large star, so very easy to resolute, but still you won't be able to do this with a normal telescope. And here in the very large telescope, there's a plot how it is achieved that the wave front of the two primary mirrors can be combined. So you have to have a mechanism where you can regulate the distance from the primary mirror to the interference pattern exactly, which means as part of one single wavelength that of the light you're using. That's why it's easier for radio telescopes than for the visible range telescopes. But these days people are able to do that. So the ghost of the telescope we discussed more or less is now in the Very Large Telescope and the Keck telescopes. And thanks a lot for the attention.